There is no minimum distance requirement for a ground fault circuit interrupter or GFCI breaker to safely operate a load. GFCI breakers are designed to protect against ground faults, which can occur at any point along a circuit irrespective of the distance from the breaker itself. The primary function of a GFCI breaker is to detect imbalances in the current flowing through the hot and neutral conductors. Under normal operating conditions, the current flowing through the hot wire should be equal to the current returning through the neutral wire. When a ground fault occurs, a portion of the current bypasses the neutral wire and flows to ground through an unintended path, such as a person touching a live wire or a faulty appliance. This creates a current imbalance that the GFCI breaker detects. When the GFCI breaker senses a current imbalance exceeding a certain threshold, typically 5 mA, it quickly trips the circuit, interrupting the flow of electricity and minimizing the risk of electrical shock. The speed at which the GFCI breaker trips is crucial for preventing serious injury or death. These devices are designed to trip within a fraction of a second, often as little as 0.3 seconds, which is fast enough to prevent electrocution in most cases. The location of the ground fault relative to the GFCI breaker does not affect its ability to detect the current imbalance. Whether the fault occurs a few inches from the breaker or several hundred feet away, the GFCI breaker will still trip as long as the current imbalance exceeds the threshold. The effectiveness of a GFCI breaker depends on its ability to accurately detect current imbalances and trip the circuit quickly. Several factors can influence the performance of a GFCI breaker, including the quality of the device, the integrity of the wiring, and the presence of electrical noise. High-quality GFCI breakers are designed to be highly sensitive and reliable. They are typically subjected to rigorous testing to ensure that they meet industry standards for performance and safety. Poor-quality GFCI breakers may be less sensitive and more prone to false tripping or failure to trip in the event of a ground fault. The integrity of the wiring is also critical for the proper functioning of GFCI breakers. Loose connections, damaged insulation, or other wiring defects can create unintended ground paths that can interfere with the GFCI breaker's ability to detect genuine ground faults. It is important to ensure that all wiring is properly installed and maintained to minimize the risk of electrical hazards. Electrical noise, such as electromagnetic interference or EMI, can also affect the performance of GFCI breakers. EMI can be generated by various sources, including electronic devices, motors, and fluorescent lighting. In some cases, EMI can cause GFCI breakers to trip falsely, even when there is no actual ground fault. To minimize the effects of EMI, it is important to use shielded cables and filters to reduce the amount of noise in the electrical system. GFCI breakers are commonly used in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The National Electrical Code, or NEC, requires GFCI protection for receptacles located in these areas. The NEC also requires GFCI protection for certain types of equipment, such as portable generators and cord and plug-connected appliances used in damp or wet locations. In addition to GFCI breakers, GFCI receptacles are also available. GFCI receptacles provide the same level of protection as GFCI breakers, but they are installed at the point of use, rather than in the electrical panel. GFCI receptacles are commonly used to replace standard receptacles in areas where GFCI protection is required. When installing GFCI breakers or receptacles, it is important to follow the manufacturer's instructions carefully. Improper installation can compromise the effectiveness of the device and increase the risk of electrical shock. It is also important to test GFCI breakers and receptacles regularly to ensure that they are functioning properly. Most GFCI devices have a test button that can be used to simulate a ground fault and verify that the device trips. If a GFCI device fails to trip when tested, it should be replaced immediately. While there is no minimum distance requirement for GFCI breakers to operate safely, there are some practical considerations to keep in mind when designing and installing electrical circuits. Firstly, it is important to minimize the length of branch circuits to reduce voltage drop and improve the efficiency of the electrical system. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the beginning of the circuit. Excessive voltage drop can cause appliances and equipment to operate efficiently or fail to operate at all. Secondly, it is important to ensure that the conductors in a circuit are properly sized to carry the anticipated load. Undersized conductors can overheat, which can damage the insulation and create a fire hazard. The NEC provides guidelines for determining the appropriate conductor size for different types of circuits and loads. Thirdly, it is important to protect conductors from physical damage. Conductors should be installed in conduit or other protective enclosures to prevent them from being damaged by impact, abrasion, or other hazards. Damaged conductors can create short circuits or ground faults, which can pose a serious safety risk. GFCI breakers are an essential safety device for protecting against electrical shock. By detecting current imbalances and quickly tripping the circuit, GFCI breakers can prevent serious injury or death. While there is no minimum distance requirement for GFCI breakers to operate safely, it is important to follow proper wiring practices and install GFCI devices in accordance with the manufacturer's instructions and the NEC. Ground fault circuit interrupters work by monitoring the current balance between the energized conductor and the neutral conductor. Normally, these currents should be equal. If a difference of 5 mA or more is detected, the GFCI trips, cutting off power. This happens very quickly, typically within 20 to 30 milliseconds, fast enough to prevent a dangerous shock. The location of the fault along the circuit does not affect the GFCI's ability to detect the imbalance. As long as the current leakage to ground exceeds the trip threshold, the GFCI will activate, regardless of whether the fault is near the breaker or at the end of a long circuit run. However, other factors related to circuit length can indirectly affect GFCI performance. Firstly, long circuit runs can experience significant voltage drop. This can reduce the voltage available to the load and cause appliances to operate inefficiently. Voltage drop is more pronounced with smaller gauge wires and higher current loads. The NEC provides guidelines for calculating voltage drop and recommends limiting it to 3% for branch circuits and 5% for feeders. Secondly, longer circuits have a greater potential for inductive reactance. Inductive reactance is the opposition to the flow of alternating current caused by the inductance of the conductors. It increases with frequency and conductor length. Excessive inductive reactance can cause voltage distortion and reduce the power factor of the circuit. Thirdly, longer circuits have a higher impedance to ground. Impedance is the total opposition to the flow of current in an alternating current circuit, including resistance and reactance. A high impedance to ground can limit the fault current available during a ground fault, potentially delaying the GFCI's response time. This is generally not a concern with modern GFCI breakers, which are designed to trip with very low fault currents. While the NEC does not specify a maximum circuit length for GFCI protected circuits, it does impose requirements for conductor sizing and voltage drop. These requirements indirectly limit the practical length of circuits based on the load and wire gauge. The NEC provides tables and formulas for calculating the appropriate conductor size for a given load and circuit length, taking into account voltage drop and ampacity. It's also worth noting that certain types of loads, such as those with electronic components, can generate harmonic currents. Harmonic currents are multiples of the fundamental frequency of the alternating current power supply. They can cause overheating of conductors and equipment, as well as nuisance tripping of GFCI breakers. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or oversized conductors. Therefore, while there is no specific minimum or maximum distance for GFCI protected circuits, it is important to consider the potential effects of circuit length on voltage drop, inductive reactance, and impedance to ground. Proper circuit design and conductor sizing are essential for ensuring safe and reliable operation. The 90-foot distance you mentioned is related to specific instructions for arc fault circuit interrupters, or size, and not GFCI.